Okay, welcome back. We resume now the workshop. We have a second presentation on our second part of the workshop about innovations that have been developed in the project. We have with us Guilherme Graça again, presenting us methodologies to do self-calibration of digital twins that are used then in the platform for services to support the functioning of services. So, Guilherme.
Thanks, Pedro. So I have a presentation on using SATO's capabilities to provide self-calibration of digital twins of the building. I was just thinking, and I'm very confident that I will be presenting the frontal lobe of SATO. So we are now going a bit deeper, of course, and now we're at the brain level, and this is the frontal part. I don't know what it does, but you'll see. I challenge the next presenters to find the body parts of SATO that they will be presenting. That's me, so I'm working with all of you in the project. This is when I was in a private building, starting a great project. I was really happy. So the idea of this presentation is to see an interesting application of our work. It's not new, but it could be very important, and it's related to the idea of a digital twin, which I think you're all familiar with it, and the application of a digital twin to the area of buildings, and how this application actually works in the area where SATO is supposed to deliver its impact. The building on the last presentation by Miracle, what we are working on, and what can be quite relevant is how can we create a self-digital twin? So building on the self-discovery. The reason why the self is so important in SATO, well, it starts because the call asked for self-assessment, and I think it was actually a really good call, in my opinion. And because it will ideally work with limited human operation or interference. And of course, that's very valuable because it's cost effective. So if things happen automatically, we can save on investment of actual human resources. And in particular, when we think about a digital twin, the idea of creating a calibrated model of a building is not new. There's many instances of good calibrated models of buildings. Many, I would say 50, so not thousands. But they were obtained with very, very high investment of human resources, and often specialized human resources. So of course, if when we're trying to build a calibrated thermal simulation of a building, if we were to measure every parameter that goes into the model, or fine-tune that parameter by hand in the simulation, and compare the results with the measurements, we would have a high-quality digital twin, and we can do that today, and people have done it, but with very high requirements of expertise and human investment. And that is not realistic in light of the quantity of buildings, of the diversity of buildings. So every building is different in terms of service and commercial buildings, and also residential. And so you can't really replicate much if you're working by hand, and the investment is very large. So it makes sense to investigate a self-calibrating digital twin. The whole calibration process of a simulation there are different ways of performing the calibration that we can work on, but the most basic is, let's say, the simulation model predicts 90 kilowatt-hour per square meter per year of overall electricity consumption of the building. Our bills show the electrical actual running of the building running. The bills show 80, So we just apply a factor of 8 divided by 9 to our results, and we call it the calibrated models. That's the most basic version of model calibration. The most sophisticated and work-intensive is going around all the parameters, measure them, put them in the simulation, look at all the building schedules, usage, and have the right number come out to begin with, without an ad hoc calibration factor. What we're trying to do with this service is to perform that automated calibration using the SATO capabilities. And so, for that purpose, we work on a room-by-room basis. So our approach is, I've just described this whole different levels of calibration. And the approach that we're using is exemplified in this figure, which is a little bit hard to follow. But the idea is, as you've seen with the other presentations, we have the real building, we have a Cypress BIM model, because that's our partner. This model has a layer with thermal zones for thermal simulation, so that's, we're coming down in terms of, let's say, realism of the model into a much simpler thermal simulation model. And this is the thermal simulation model with several zones that we will be automatically calibrating. Now, how do we do this? What's the secret? So the secret is, so what makes our calibration new? It has more requirements, so our calibration is more intrusive. And I think it's important to say this because it adds credibility to our claims. If we were able to calibrate by doing exactly what other people were doing, it would be not so credible. So what we need to do in the middle here is, whenever the rooms are not occupied and we're not bothering the building occupants, we need to actuate into the room and, for example, heat the room and then look at the temperature decay, and in this way measure the heat loss coefficient between indoor and outdoor. This is one example. So we have a set of these virtual experiments, which in fact are the assessments of SATO, or some of the assessments of SATO, and then we use the results of the virtual experiments. In this case, it's Energy Plus thermal simulation model, and on a zone-by-zone level, we calibrate the model. You have here two like cartoonish depictions of calibrations. So in a room, we will turn the heating system on, raising the indoor temperature. Then we turn it off. We look at the decay of temperature. We fit the best U value for the external heat loss to the decay, and that's how we extract an as-built U value for the room on a room-by-room level. We also do that in another assessment to identify the thermal inertia of the space and the furniture. These are also kind of unknowns in many buildings, and in fact, these virtual experiments measure as-built effective thermal inertia. This is something you can't really get from design data. So we think that this is very promising. We do the same thing, the same approach in different areas. For example, here is the work of Frederico, Nuno and João are working on these sites. These are postdocs and students, PhD, that are also in SATO, will be presenting later. So the heat pump, we focus on measuring the ratio between the actual COP of the heat pump and the theoretical Carnot COP. So that will be a parameter we focus on, which is the efficiency of operation of the heat pump. And with this efficiency, again, we bring this coefficient into the simulation and we obtain a self-calibration of the heat pump component of the system. So this is done whenever there is an opportunity to perform a digital experiment or an assessment. We do it, we take the coefficients, bring them to the simulation, and we claim that we get more precision. This is an example of the parameters that we extract at room level. So heat capacity of the walls, furniture, heat loss to the outside are some of the examples. and the ratio of CO of the heat pump performance. I'm sorry here about the superimposition. And then, as we, of course, we then bring this to a model, as discussed, on a zone-by-zone level, and we compose the whole overall building model. We're using Energy Plus, although that's not the main point, but there's a connection already between SIPE, which is our BEAM platform, and Energy Plus, so it makes sense. Because, of course, we are at the end of SATO and we have pilots, we already have some examples of this, the actual performance and capabilities of this approach. So we perform the calibration, we update on a zone-by-zone level the model, and we obtain a digital twin. There's some formatting issues, but it's fine. So we have inspections, which are our assessments. They calibrate the twin. And then in terms, for instance, of energy performance, we are able to update theoretical EPC to an as-built EPC using the calibrated model. And now let's look at the application of this in the pilot. In some of the pilots of SATO, some of them are residential. We have focused on detailed multi-zone thermal simulation for commercial buildings. As for residential, it's not the common approach. It's too heavy at the moment. And so what we show you are applications in pilots, and then you have 4 levels of calibration. So you start, well, the line number 1 is the measured temperatures in the building. Line number 2 is a simulation, let's call it standard. Number 3, we bring in the self-calibration at room level. And then in number 4, we bring in the HVAC calibration. The HVAC calibration has, you can see it in 2 places. You can see, because we are able to measure the effective heat delivery and removal of system HVAC. So you get a better depiction or simulation of the room temperature profile when you turn on and off the HVAC, because we actually see how powerful it is in a given room. That's one level of the HVAC enhanced or calibration process. And then at the thermal plant level, if we calibrate the HVAC model, we of course have much better predictions of electrical energy demand of the building as it's being used. So we have 2 examples. This is an office building that one of our partners. This is in Seychelles. We have one zone there where we have enhanced monitoring with SATO. We have the whole building, but then we have a particular zone where we also, the municipality installed new operable windows as an investment, so they're exploring. They're already installed in this zone. We have new windows, they invested, and then if it works well, they may consider extending to the whole building, as this is a great building to have operable windows, and also a great climate and very peaceful neighborhood to do that. So we hope to have a good effect here. And so the example of application from level 1 to level 2 is going from the purple line to the dark orange yellow line, whatever that color is, where the measure is red. And so in a standard, let's say, in simulation model, you have issues with the effective thermal capacities of the zone that we are able to pick up by performing these experiments that give us the calibration. And then you also have, this is a very, let's say, as bad as thermal simulation can be. So then it immediately changes the zone temperature very fast. This is a bit exaggerated. And we are able to pick up both behaviors better. Then as we add a finer fine-tuning of the automated fine-tuning of the room HVAC, we get to the other levels of the calibration, where we have really, really quite excellent fit of the temperature. Let's automate it. And then we have improved fit, not perfect, right? Of the electrical demand, where the data is red, and so Frederic, we are green, right? So we're not perfect. Okay, nobody's perfect. So that's where we are. The other example is our library, which you've seen many times, and I'm even embarrassed because I think the colors of this building are just embarrassing with the yellow and the blue, but she's back. And in the library, SATO has triggered an investment of, again, operable windows. So we have a lot of motorized windows at high level, low level, automated, connected to SATO, controlled by SATO. And I've shown you this morning some results of energy savings of the control of this building with the SATO aggregated control. That's what I was showing you this morning, the little bars and all the savings. Those are preliminary results. Here again, we have the calibration, where you're going from a standard simulation, that's purple. And then as you add the room calibration parameters, you go into the dark orange line, the red being the data. And then as we deploy the HVAC level calibration, we move into the green line, which is excellent in my perspective. Better, it would be suspicious, so you don't want to go too far. And then for the energy consumption, in this case, we also have a better agreement at the moment. That's the lower chart compared to Seychelles. Overall, where we are with this service is, in our perspective, we reached a good point with it, and we see a really good potential for energy optimization, energy refurbishment, and of course the whole idea of being autonomous. And that's where it connects to the discovery, because what Vinicius and Miracle showed related to self-discovery, you also have self-discovery of the capability of performing these experiments and when. And so this looks really nice as let's say, something to be continued. So thank you very much. Ainda temos tempo agora.
Thank you, Guilherme. We'll take questions now. The audience or online, please.
Yes, I have a question, because now, of course, you have done two specific calibrations, one on the room properties and one on the HVAC properties. And then I would say, of course, then the results on these two issues are reflected to be quite accurate, because this is where you did the calibration. But what about other parameters where you did not do calibrations? How do the model perform on these parameters? Does it also improve those parameters? Like I would say indoor air quality. Is the model now calibrated so it actually can do the indoor air quality?
Have some efforts and some measurement events the idea that, so to make an answer to the question, we are not able to perform a calibration. I think also commenting on your question, and the important thing is the self.
Yes, but we should be aware that the calibration is only valid for the issues where you have done the calibration. It doesn't mean that the model generally is validated.
Okay, thank you. Any more questions? No? Then let's proceed with the next speaker in our innovation session in this workshop. And now we move to a PhD student, Zygimantas. It's really difficult for me to pronounce the surname, so sorry. You can announce yourself. So the work that we are going to present now, it was actually a challenge that was raised by our project officer when we were in the grant agreement negotiation stage, right before signing the contract. And it was about designing or developing methods that could be used to assess the real-life performance of appliances. So what Zygi, as we call it, will present is about this work and focusing on clothes washing machines, actually.
Thank you for the introduction. While I was listening to other presentations, I was thinking for the analogy of we have the brains, we have the heart. So perhaps that could be a good analogy. Okay, so I'm going to present just a brief overview. We're not going to go appliance real-life assessment. So without further ado, as we know, the appliances, they consume a lot of energy amongst the total household energy consumption. So to mitigate this problem, of course, European Union for the consumers to and also it creates this initiative amongst manufacturers to make more efficient appliances. But there is a problem because the labels are quite static and they do not really consider real-life factors. So this is the main problem. And it doesn't consider the real utilization, operational factors, for example, in let's say washing machines, you can select multiple programs with multiple temperatures, environmental conditions. So, for example, how appliance is affected by the ambient temperature, because sometimes people have washing machines, let's say, in the balconies even, sometimes inside. So, how does this affect it? And of course, the user-appliance interaction, it's not considered. Like, for instance, this is the problem. And to work on this task, we have some limitations. Okay? So the first limitation is that there are no data sets available to actually work with it. So we had to create our own data sets. Of course, there is no definition of what is actually a real-life assessment. Main keys in this presentation. So, starting with the lack of data sets, we started, of course, with the data acquisition, and we are measuring in the laboratory and in the household, acquiring the data. Okay, so we're acquiring environmental data, temperature, humidity, operational, so acceleration. We have water flow in and water flow out of the machine, so basically the consumption of the water. The water temperature, we measure it through, I will explain this later. We also measure drum temperature, the door temperature, so we attach basically the sensor on the door of the washing machine, let's say. And the energy, of course, we have some measurements like current, power, voltage, frequency, and power factor. In the laboratory, this is done in the, let's say, we are using a protocol. So when we are acquiring the data, we label the data like what was the temperature set in the laboratory while we were doing that. And of course, the programs that were available on the machines important. So it's so a little bit of parameters. We have one on the top and the side on the back. We have the current sensor. We put the sensor on the door, and we attach one on the drum. And we also have the water flow sensors, and we attach the temperature sensors on top of the pipes to basically try to measure the water temperature. For the dryers, it's a little bit different because we put the temperature sensors and humidity sensors inside the lint trap chamber. And of course, we also have the current sensor and the accelerometers. Just a little bit to show how it looks like in the laboratory. This picture is actually old because actually currently the accelerometer is in the middle. And here you have water pressure sensors and water flow sensors and all that. So this is basically the setup in the laboratory that we are working with. To control the temperature in the laboratory, we have like a big AC unit while we are doing the data acquisition. Okay, so this was the laboratory part. And we also deployed in the SATO pilot the acquisition boards. We developed a data acquisition kits that were smaller version, let's say, of the acquisition platform that we have in the laboratory. And of course, we use exactly the same sensors, the same acquisition frequency, to replicate as close as possible to what we did in the laboratory. And then, of course, all this data is being sent to the SATO platform. So this is how the acquisition box looks like. Box, and in the right we already closed it. Of course, we didn't leave it open because it would be hazardous. Okay, so talking about the overview of the data set, we already acquired over 800 cycles, and we are currently acquiring more of them. So let's say it's 800 plus because I really don't know the exact number. And this is just to show you how it looks like, for instance, one washing cycle. We have the energy consumption patterns, then we have the water consumption patterns, which one, the blue one is the inlet, the orange one is the outlet, and the temperatures, the varying temperatures, so we have the room temperature, how the temperatures vary between the inlet and outlet pipes. Okay, so this was the dataset part that we were working on. Now let's go to the real-life assessment. So what we can do with real-life assessment? We can do reference assessments and real-life assessments. What are those? Reference assessments, basically we can use the data that is available for us from a Perl dataset to basically compare like baselines of what we are acquiring and what is registered officially in the Perl dataset. And then we can do the real-life assessments. So based on the data that we acquire, we can do, like, for instance, resource and service provided KPI. And of course, the resource consumption, so how much water it was consumed, and how much, for instance, the environmental impact, which would be like a CO2 produced. So how we can do these real-life assessments? Of course, when we gathered enough data, we started to basically look into data to explore it, let's say, to see what's going on. Because to calculate the key performance indicators, we need to know the weight of the clothes that was put in the machine. Like, we cannot ask the user every single time to provide us this information, so we have to extract it somehow. So we come up with these up with this soft sensor approach. Okay, and here what we see is from the data analysis that it's the first rinse of the washing machine quite well represents the weight that was inside the washing machine. Almost, it's a linear model basically. So we worked on two approaches of how to extract basically the weight in the washing machine. That was the first approach that I was mentioning, that basically we use the first amount of water that was taken in at the first rinse. Then we apply machine learning models to extract this information and to basically laundry loads estimate the laundry load. The second approach was to try to do basically the same thing, but using only energy consumption data, so not including the water consumption. Because the idea is basically to try to reduce as much as possible these additional sensors, and ideally just to plug the appliance to a smart plug and have all these assessments done for us just based on the energy consumption data. So in terms of KPIs, what do we have? We have two main KPIs. So, for example, water consumed per kilograms of load of laundry, and the energy consumed per kilograms of laundry load. Okay. So these are the results from both approaches. The first one is based on the using the water, first rinse water amount to extract the kilos that were put inside the washing machine. And the second approach was using the So right now, the second approach is a little bit worse than the first one, but we have some ways to mitigate these, let's say, false estimations that I will explain a little bit later for you. And these are basically the results of already calculated KPIs. So you have the ground truth, sorry, and the predictions of the KPI. So if we have the energy KPI and water KPI. Right. So we do have a mobile application developed, and the users that are participating in the project, they have all this information available to in the mobile application. So why is it good? People can basically compare the washing practices, for example, how much depending on how much clothes they put in the washing machine, what kind of program they selected, for example, what was the impact on how much water they consumed, how much energy they consumed, how well the machine was performing in terms of the KPI, and this can basically help users to decide better practices of selecting their or making their washing practices at home. What else? So, for the conclusions, we created this system to acquire and support the laboratory and household research for real-life energy efficiency, and it resulted into the data set that it's going to be publicly available. So then, of course, we also defined the real-life appliance energy efficiency, how we can calculate it and to present. We have the models that performing fairly well to estimate the laundry load. It is actually very important to calculate the KPIs. And we developed a mobile application that helps consumers to basically do the optimized choices, let's say, or to help users, to guide them to do the better choices in terms of their washing practices.
Okay, thank you. Questions?
For the presentation, the app, does it have fault detection capabilities, or will it have in the future?
hopefully it will have. Right now, not yet. But just to complement, we do have data for the appliance, and we do have some data for exactly the same health appliance, so we can try to work on that. And it's in progress, but right now it's still not available for the user. But for example, to add up, imagine your machine is functioning well, you can track all the records over time, but then suddenly you have some weird water consumption or weird energy consumption. So actually user itself already can kind of identify that something is wrong with the machine. Sorry? Yes, the data will be available. All the data will be available soon, and we are going to publish it in Zotero, including the publication. As soon as perhaps next month.
Nothing else? Right, let's move on. Thank you, Ziggy. So our next speaker is Konrad Diwold from Siemens, and he will be presenting to us dynamic ways of updating the smart readiness indicator that were implemented also in the SATO project.
Check. Okay, that works. Hi, everybody. Okay, analogy to the body. I think that all these assessments that are taken in SATO, or provided by SATO, are basically biomarkers. So what we are trying to do is then to get it in some sort of a format that is understandable for the patient. So, Konrad, drink less alcohol, or stop smoking. This is basically what the smart readiness indicator is, I would say, for building. So forgive me my ignorance that I'm showing you the next slide at this conference, which is called Sustainable Places, because I guess we are all aware of that a lot of energy is consumed and used in buildings, and that we have to get our emissions down. And that's why the European Union really tries to reduce them by 2030, and we are trying to become decarbonized, especially in the context of the building stock, by 2050. So in order to do so, the smart readiness indicator was introduced, and that's a framework that is going to be used for rating the smart readiness for buildings, because things like SATO and other projects and methods that are basically presented here help to optimize the building consumption. As we've seen before, if we control when we open or close our windows, we can drastically reduce the energy used by the HVAC system. So that's something that will help us to reach that goal. And currently the SRI is in a testing phase, but it's going to become mandatory in 2026 for buildings of a certain size. And what it does is it basically assesses a building's capability in three main domains. So on the one hand, we're looking at the energy efficiency and the overall in-use performance of a building. Then what's also necessary, or these days, is that we can adopt to what the user actually wants from the building. And the last thing is basically the integration of buildings into our energy system, because basically they're batteries, and we can use them, for example, for peak shaving or participating in energy communities and all these kind of things that further help us to make things a bit more optimized. So basically, this assessment is done in a building based on 9 technical domains and 8 impact criteria. And you can basically see here an example. So basically, we have functions that can or cannot can be present in the building, and they can be present in the building at certain levels. So we start at level 0, which is kind of the least smart way, so to say, and level 4 is the smartest way. Here we have heat emission control, and heat emission control level 0 is that we have no automatic control, And level 4 would be that we have individual room control with communication and occupancy detection. Now, how do we come up with the smart readiness indicator of a building? Well, basically, we have for now an Excel, so there are several versions now, and we take the building operator and an expert, and they assess the building. They have a look at the documents, they have a look at the building models, if there are any, what appliances are in there, and they basically rate the building, and they go through all these functions that are there, and they basically then assess whether or not a function is present and at which level it's present. And they, of course, also have to specify where's the building located, what's the use of the building. This all kind of comes into when calculating the SRI. So we have this done for all the pilots that we had in SATO at the beginning of the project. But this is something static, right? This is something that you do once, and you don't want to do this every year, because this costs time and effort. How can we get from something that is currently static and maybe done once to something that can be performed continuously? Well, what have we got? As I said before, we have continuous assessments of the building. So we have biomarkers, I would say, of the building. This is something that is kind of the core of SATO. So we have these assessments, and then based on these assessments, as pointed out before, we have services that will then reinforce optimization, which are performed manually, and we kind of have to match them somehow. So this is basically what we did. So what we can do is we can look at the assessments and, of course, at the services, which are accumulating several assessments together and then using them in order to optimize the building, in order to see what SRI domains and services they actually impact. And this is something that we did. So we basically went through all the smart service functions of the, so there are two ways of calculating the SRI. There's a simple version, there's a complex version. We took the simple version because it has less functions. But what we can do is we can basically assign SATO assessments to a certain function. Say, if this assessment is present in the building, then we can assume that this building has a functionality level for this respective function of, for example, 2. This is one way of doing it. Another way of doing it would be to say, if this assessment is present and we get a certain value out of it, then this indicates a certain functionality level. And as we have services, and as we have heard before, services basically aggregate different assessments together in order to perform optimization. It's not, how to say, we might need to accumulate a number of SATO assessments in order to derive a certain SRI functionality level for a specific function. And this is basically what we did. And what helps us here is, this has been mentioned by Miracle before, that we have semantic interoperability. So basically we have a semantic core, we have a knowledge graph where all the information is stored, and we can tap into that and integrate, right? Because we know how the data will look like from a task that performs an assessment. So this can be represented in here. And basically this will do the magic for us. And that's why I think semantics is such a great benefit in the context of this. Now, this is basically where we're starting. And once we have this link between the services and the assessments, well, then we can do a recalculation. And we can basically do that whenever we please to do so. And what I've shown you here, I'll just go back. So let's consider, and this is a very coarse example. Let's consider that the expert looked at the building and said, well, based on what I see in terms of appliances, we have level 4 because we'll have individual room control and occupancy detection, and those things work together. Let's assume that, okay. And now the building is in operation, and we basically see that heating is not really linked with occupancy detection. That these things, while they are there, they're not really used. So while the indication of the appliances in the house or building suggest a readiness level of 4, actually in use we see it's not really there. This is basically what I meant before, giving us some feedback and telling us, hey, do something. Because maybe there's something wrong and we basically have to check to level 4. So how do we calculate? We're back at the semantics. So basically what we decided to do was to use semantics to do the calculations. So as I said before, the SRI is currently in a test phase implementation with Excel sheets where we can basically put in the information. But this is, for a computer scientist like me, others of you, kind of not really satisfying. So there's a lack of standardized information model exchange. And this is how to say, version them properly. So a better way of doing that in this concept, and this also ties in perfectly with the SATO core, so to say, is to use semantics to do so. So basically derive a semantic model that incorporates the core concepts, also all these things concerning different national specific services and regulations, and allows us to calculate this. And with this, we are able to calculate SRI automatically, and it's transparent on how that works. So basically, here's just why this is a cool thing, so to say. It makes things then fairly easy and really integrates well with what we have in the SATO platform, because we don't have to fill out anything anymore. It calculates and we know why it works. And the nice thing is, for the future, it's also easily integrated with other existing building models, such as bricks, OT, and so on and so forth. So just that you get an idea of how this looks like, this is basically the vocabulary. So we have the names. See color-wise. So we have things that are basically present on the then we have things that concern the assessment, but we also incorporated here national regulations, which is quite important because, as said before, it makes a difference whether or not your building is located in Spain or in Austria. If you're interested in that, here's a reference. So this model has been published, so you can have a look at last month at the Semantics 2024, and it's open source, so you can use it. Okay, now this is basically what we have done. Now, how is it working in the system itself? So what do we need? Initially, as said before, we need some sort of a baseline SRI. For this, we can use an SRI that was performed, an SRI assessment performed for a building. So we have here an Excel sheet. And what we also need, not necessarily in Excel, but in some sort of format, is we need this link between assessment and SRI. Inputs that we require, and what we're doing now is we're uploading them to the SATO platform and then converting them into an ontology and store them in the SATO knowledge graph, and there they reside. Is that at regular intervals, we don't have to do that too often. We can do it every month, every half year. We are basically retrieving the information stored in the knowledge graph that represents the SRI calculation of this building. RDF, so that's again adapted because things might have changed. Maybe something came into the building. What we are doing is we are retrieving all the assessments that are present in the building, and then we can match them because we have this link between assessments and SRI. We can basically check, is the trick file that we have still is it still okay, or do we have to change it? Right, so if the trick file is outdated, then we of course have to update our trick file according to what we got from the system. We can recalculate the SRI. We can store the results for the user to see what's actually going on and that things changed. back the information of the new trick file. So basically, we will update this SRI sheet, so to say, but of course in a different format. Automatically, and will always give us an updated version of the SRI. Here's basically, again, there are now nicer visualizations for that. Just to show you. Now the condensed information for the user with basically all the scores for the different domains, as well as a summary. So that's there, and we can of course show it nicely to the user. Still the way that they ought to be, or if they changed. That's all from my side. Thanks so much.
Thank you, Konrad. Questions, please?
Not at all. That you have or this didn't change. So, for example, the SATO platform has visualizations.
No, we in a previous presentation before the coffee break, where we were exploring the interfaces that we use in the SATO project, we had there one. I can show you one screen where this is shown. So here, what you see is actually the output of correlating all this information. The overall score that you get, which I think also conveys the idea of how capable your building is of integrating smart services for flexibility, for the potential for energy efficiency. That I think that is the.
Thank you very much. Thank you for your presentation also. I have one question. How do you instantiate your knowledge graph initially?
Yeah, we have kind of an ontology that represents.
It done manually, or do you?
No, automatically. Everything is done.
You need a certain quality of your Excel sheet, I guess, yeah? Okay.
Also a finding when we tried to basically build the ontology, because we have to dissect the whole thing to see how the calculation works.
Okay, thank you.
Thank you. More questions? We do. Okay. Okay, then thank you again, Konrad, for your presentation and for the discussion. We move to the last part of the workshop, where we will have a discussion here, a panel discussion. And this is centered on the current challenges that we can identify to smart innovations and smart self-assessment and optimization of buildings. So I would like to invite Per Heiselberg and Guilherme to come here to the table and start this discussion with me. And I think I will try to trigger it from one point of view that I've discussed with Guilherme many times, in one of the challenges that we actually experienced several times in the project while setting up the pilots, actually, which is, and I think this challenge lies somewhere in the connection or the bridge from hardware to software. So we can make all these smart assessments and all these automated calibrations of digital twins, many different techniques that then enlighten us on the actual real performance, energy performance of the building and the building itself and the equipment. But how to make these things quite general and scalable that could be deployed at a large scale is something which is tricky. We've seen also today that interoperability, all those semantic descriptions, and they help on doing that. But it looks like there is also still something missing, because when we deploy something like SATO on a new building that we have some descriptions, sometimes it seems that the adaptation from the work that was done is not still. And why? Because I think the hardware. So generalizing the hardware, the measurements that are done, and the capabilities of the system. I would say this is the first, at least, challenge that we could to trigger the discussion. I will pass the word either to Per or Guilherme if you want to say anything about it.
Because, of course, the requirement for this to work is that we have reliable data. And I think the experience from a lot of the pilots is that, of course, we do commission buildings, but we usually do not commission them to a level where we actually evaluate if the sensors are located in the right places, if the sensors are giving the right data back. And I think in many cases we found out that there were sensors which were faulty, sensors were located not in the right places, giving the right information back, and so on. So there is I would say, a kind of commissioning process that you need to do when you want to apply these, you could say, more advanced methods to automatically assess. There is before you can do that, there is a commissioning process you need to go through to make sure that the quality of the data and the information is right. Not just plug and play, unfortunately.
Summarize that as the quality and reliability, the continuous quality and reliability of the data. It's one factor that should be taken care of.
To add on the difficulties that have been discussed, what we found in SATO's pilots is not only is the hardware a barrier because it physically needs to be connected. The second level of barrier is once we have the hardware connected, we now find, let's call it a safety concern barrier. So you have the networks of the buildings as, let's say, fortresses where data cannot come out, external commands cannot come in, and that's a huge concern for the deployment of these systems. So either they go into a separate kind of dumb network, which would be perfect for these systems. They don't need let's say the common internet. They don't require all that data flow. And so as they go into the common or whatever we could call internet, we come into all these security concerns, which are still at the moment interfering in some of our pilots, which is even in the context, of course, of a research project. So that's quite, it's really a big barrier. I don't know if anyone wants to comment on this from the audience.
Yes, I noticed several people in the room that are not from the project. We would also welcome experiences and comment on real challenges to adopt these more innovative approaches.
My name is Filipe Silva. I'm part of the project as well, but I was working with residential pilots in Portugal, and I think if I share what was our main difficulty, I think is once we install the sensors, and Per discussed a bit about the placement of the sensors, sometimes we don't have much control about the placement because people only have power plugs in that place, so we need to do it in that place. Or people sometimes after we left, they change it to a different place and now we don't exactly know where it is. So I think besides these barriers on data security, technology, there is this human barrier that is very difficult to overcome, which is to convey to the people how these systems will work, what they can get out of these systems, advantages. And I think this was one of the main struggles because these projects take a long time. So from the time that we initiated monitoring until the time that we gave something back to the people, it takes very long. And people start to ask questions, they lose motivation. So I think this was a very big struggle.
This is also something that we share in SATO in our showing results from our Seixal residential pilot near Lisbon. And many things happen once you deploy things there. So again, the quality, availability, and reliability of the data, it varies. It's quite difficult to control. I would throw a second topic here, which is connected to the first one. We've heard Miracle, Konrad talking about semantics that help describe the systems, the processes, they help automating. Actually, I think I was not a big fan of semantics for data description and data sharing and so on before, but I recognize the value for automating all the processes in these platforms, describing the systems. There are lots of possibilities of using semantic modeling for that. And this, sorry? It's describing the properties. Mainly it is describing the properties and the relations of concepts that are part of your system. So devices or tasks, like sensors, or it's a framework. Yes, either abstract components or physical things, and the relations that exist between them. A bit, yes. It's a bit more than that, actually, because of the relations between them. But I was going in a direction which is, and we have Konrad from Siemens, maybe he has a view on that, I don't know if you can share it. But I think all the manufacturers, vendors of all the systems that exist in buildings, they have their own approaches, their own systems, the software that they want to deploy, all of that. And this brings a real interoperability problem because many of these systems are a sufficiently part or big part of these systems are closed. Okay, so it's very hard to operate them or to change their operation or condition. It's quite difficult. And I'm wondering if it would make sense at the EU level, for instance, that there would be like minimum requirements on all these systems on the openness of certain functions, for instance, in connection with the smart readiness indicator. So the smart readiness indicator conveys information from different levels, different domains that exist in the building. Should there be some minimum requirements on available APIs that would allow interaction with these systems? I'm not talking about forbidding all the manufacturers of doing their own things and having their own products, but a minimum layer that could then be explored by third-party services. I see it as one path that could be followed to mitigate all these difficulties in developing innovative things that can eliminate one barrier. Anyone wants to give an opinion on that?
Hello, I'm Caterina Calefato. I'm a UX and UI expert and a European project manager, and I follow the question of the colleague. Considering that during the project you developed the whole infrastructure, so you focus on the hardware, then data quality, the semantics, I would like to know if you are considering to add in your exploitation plan for the scale up a more wide job about user interface, also considering the scale up of solution providers like Siemens in other sectors that can be not for the consumer, but for example for the energy monitoring of an industrial kitchen, in which you have other type of problems, so you cannot use the mobile app. You have port devices connected, port devices for the graphical rendering, connected with PLC in a kitchen with people wear gloves, have lighting featuring, and they are not energy experts, but are people who cooks, and they are required to use their appliances addressing the energy constraints that the management gives them, but their task is to cook, not to handle energy profiles. And as a UX architect, I joined and coordinated a redesign job for a competitor of this solution, but for the industrial domain of appliances. And the job was really a wide job about UI and info visualization design. So to recap the questions, if you consider this in the exploitation and the scale up after the project, otherwise it is not possible to go to the market with a solution that is perfect from the technical point of view, but difficult to deliver to the common users that have other type of needs.
Try to answer at least partially to your question. It was a very specific application that you described. Of course, I did not fully understand it all, and what are the details, let's say, lots of details there. But I think the question was if we could deploy some of our developments in that kind of environment, then to make it easy for, you mentioned cooks, for them to get at least some idea of what is the energy impact of their practices, their varied practices. I would say it is possible, but it would require adaptation, because the use cases in many things of what we did, they are for a specific purpose, for specific buildings, but all the structure, actually, let's say the architecture of the platform that we have, it would perfectly fit there. Yes, yes, yes.
Regarding the adaptation of the platform for other scenarios, the platform, as we were describing, the semantic part, we can see as two divisions. One is the semantic applied for the domain, which we could replace, for instance, for the kitchen scenarios, and try to focus on how to describe this scenario instead of a building, let's say. And then there is the technical domain that moves the SATO platform and how to create things and execute things. That could be independent and we could adapt. The other thing is that the SATO platform already foresees different stakeholders in the user interfaces. For instance, as you were mentioning for kitchen, for instance, there is the cookers, but there are different stakeholders as well. So there is the cookers, which are like building occupants, and the interface for them is more simplified and with a summary of what matters for them. But probably the best benefit would be for kitchen manager or restaurant managers, which is another interface with very much more detail and more complex things. So the SATO platform already supports these two different levels of interfaces for different stakeholders, let's say.
There is one specific partner in the consortium that had the responsibility of part of it, and part of what we have is going to be open source. The platform, the main component, let's say, of the platform. Another approach that we have been trying is there are still subdomains, I would say, in the energy field, like flexibility, for instance, that we somehow addressed the concept that would be followed, but we did not do a lot of work apart from building as a battery potentials and so on. But we did not approach the interface of SATO with grids or with energy markets that are involved in flexibility. That is something that we try to explore, also participating in other avenue that we have tried.
I agree with you in the sense that the interfaces are, and also that there are certain vulnerabilities, and the reason is we have two types of interfaces that were discussed today. We have the web-based that interfaces with a very diverse set of then we have, let's say, a more innovative 3D-based interface on Beam. So that's already two worlds to explore. But regarding the current exploitation plan, we, within the consortium, see the two main pieces of exploitation. They are housed in the platform as an open source component with its capabilities. Second level, let's say, the assessments and services. So we are not developed enough on that side. I think we have a certain vulnerability because we cannot identify the interface because we need to, and also because we put a lot of effort on the backbone, so the data flow that you saw, and also on the assessments where we have a very diverse set. So I would say we are not as strong as we would like.
Anyone else? Any other topic that you would like to?
But it's kind of just very simple. The SRI being an indicator. Doesn't it limit what we can do in the sense that you said buildings are big batteries, which I agree, directed to that end of deploying buildings as that framework, perhaps it would be more effective that the indicator would be quantitative, actually give us some deployable flexibility. I find the indicator a bit too
potential that you have, right? And what we've seen here today, to a certain extent, it's not an indicator anymore, but it's more real, the real smartness, quote unquote, what the building really does. And I agree that at some point you might want to link, because I mean, of course you can build a building and then argue if it ticks all the boxes in terms of automation. Are kind of really important. Also something that we will look how to integrate in our ecosystem portfolios. But I mean, arguably this is something that should be addressed by
The consideration that I have is that when you have good quality data, then you can manage indicators for the end users in a different way. For example, you can use quantitative indicator to allow the user to be inside an energy profile as a goal. For example, in the case of industrial kitchen, they have some ranges that they have not to overcome because the management has some expenses to follow for the energy consumption, and the quantity indicator delivered in a way that is understandable as a goal for the user is necessary. Then there is the quality indicator that is a sort of social acceptance and perception of the usefulness of your actions. So, for example, educating people in a more aware, energy-aware behavior also at work, not only at home where you pay the bill, but when you need a more responsible action. In this case, you can use the same data or a part of data to manage and deliver quality indicator, but not in the way you ask a survey. It's a design issue, it's a big design issue to provide a user interface that allow people to do their job, the daily routine, but in the same time, this type of UI is a persuasive UI that educates and train users to a more aware energy consumption. So for this reason, I spoke about the UI, because here there is the pivotal role between the adoption or the fact that the user abandon a technology. You can do the best technology of the world, but if user don't adopt it because they are not able to communicate with the infrastructure, the semantic, the machine, the indicator, the panel, whatever, it's very difficult to scale the market.
Any comment on this? Yeah. Any additional, I mean, the idea for this discussion would also be about experience in these challenges. Okay.
Hello, my name is Federico and I'm a PhD student working for SATO. It's for you, Konrad. Some of the services in the SRI, the higher levels of functionality, depends a bit of the assessments to know if some grid signal is sending to the building manager to provide some kind of flexibility. Are you accounting for that kind of situations?
But you can, of course, also account for that specifically. You can also account for results of tasks and assessments because we have them semantically modeled. So we can basically represent that and it's kind of translated then automatically. But for now, it's basic, and this was the discussion that we had a few months back. For now, it's basically just the presence of an assessment. Because if we have an assessment that assesses, I don't know, occupancy, then we can assume in terms of occupancy detection sensors. And of course, is very conservative. So I think the links that we have for now are very conservative, and there might be even higher functional levels there. So it's really that the assessment is there. So we basically, what we do is we check that the assessment is there and that the assessment is valid. So if an assessment is there, but it hasn't been triggered for the last year, then we don't consider this assessment.
Okay. Anyone else? Any other comment that you wish to address? We are discussion. It's the right timing actually to do it according to the schedule. And if I can summarize a bit, I think there were 3 challenges that were about the data reliability that we have overall. It brings me a bit, it has a tone of fault tolerance. We need to account with many fault tolerance mechanisms to maintain running and functioning as they are expected. There is a challenge in user adoption of the systems, which has a consequence also then in the exploitation and the adoption of the systems. Which was the third challenge that was here. So what is the usability and the usefulness of the products that we deliver after the project? And of course, working on those aspects is important from the beginning so that the right target is achieved. Any final comment, Guilherme or Pedro? No, then thank you for your presence. I'm not sure if there was anyone online at any time, but thanks for all the audience here. It was, I think, a fruitful workshop. See you soon.